Unfortunately, I have to give my lecture in English, but I will try and speak very slowly. It's important, if you do have any questions, I'm here both days, so don't be shy. Feel free to come and find me. My talk is actually, the second half is a little bit controversial, but it will be, it's under review at Analytical Chemistry, so it'll be interesting to see what will happen. So before I start, I would like to thank the French Chemometric Society and Agrotech for the invitation to come to Paris, one of my favorite cities in the world, so I'm always welcome to come and visit. Probably the best place to start is with my title. I'm the director of a Center for Intelligent Chemical Instrumentation. And what that is are smart instruments that allow any person to use. They're used a lot in security, but the idea is we don't need a chemometrician or a chemist or even someone with a college education to use these instruments, and maybe not even a human. A lot of these instruments now are found in robots and drones. In fact, we had a very early paper with a drone before the term drone even existed. Back then they were called unmanned aerial vehicles. So my research involves three main areas: chemometrics, forensics. We have one of the oldest forensic chemistry programs in the United States, and a lot of work on metabolomics and proteomics. And presently, most of our work is focused on plants and doing metabolic profiling of plant materials for authentication and identification. The foundation of our presentation is something that should seem very logical to you, which is our very first experience in the laboratory. We're taught to make multiple measurements. We don't go in and run an experiment one time, and that's because we want to characterize the indeterminate error. However, in chemometrics, we have this habit of validating our methods and optimizing our methods using only a single data set and only doing it once. And what I would like to speak today about is the idea with modern computers and faster computers not to rely on a single measurement, because you wouldn't do this in the laboratory, so let's not do it with our data analysis. And the way we're going to solve this problem is through a very old technique called bootstrapping. We have also a philosophy, and this is mostly directed for students. There's always a tendency, especially when we have a shootout, to try and optimize our methods to get the very minimum prediction error or validation error. But a lot of times what we're really doing is overfitting our model to the data, and then our goal as chemometricians is actually being a fortune teller, to try and predict what will happen in the future. And if we overfit the data that we have, a lot of times we don't do very well with future predictions. So what I would like to sort of recommend, especially for the young students, is not to concentrate so much on optimization, but more on validation, testing your models, making sure the models are general and that they will work in the future. Okay, so going back to our intelligent instruments, one of the things that's required are automated or parameter-free methods. In other words, we develop MATLAB functions where we'll have an X data set and a Y data set, but no adjustable parameters, no latent variables to optimize, number of principal components to modify, and if you're working with support vector machines, no cost function to optimize. We like this all to happen automatically and transparently. And this is good because we can put it in things like robots, and people can use this. And we first got involved with this doing ion mobility spectrometry, which is an example of a smart instrument. This is not science fiction. It's very easy to spot a smart instrument because they usually have two lights, a green light and a red light. So this way, when someone sees the red light go off at the airport, they usually know to do a careful inspection of your luggage. So some examples of the ways we do this is classically we usually have data for calibration or building our model, and then we have a second data set for optimizing the parameters, and the third step is we have a third set of data for validation. And what we've done is we back in probably the last time I worked in France, in Marseille, with Nathalie Dupuis, we developed an automated version of partial least squares. And now we like to call these super partial least squares and super support vector machines. We incorporate this step inside the algorithm so that when we put in our calibration data, it will divide the data set up and do this multiple times to optimize the parameters. So this way, we don't have a user trying to adjust the parameter. It will occur automatically. And the other key idea, and I'm going to discuss this a little bit later, is this idea of latent partitions. And this is basically on how to divide the data set up so that we retain the statistics and the probabilities of our experimental design in the training set or calibration set. The bootstrap, and here is Baron von Münchhausen, is where it gets its name from. He is on his horse and he's stuck in a swamp, and he's pulling himself out of the swamp by his ponytail, which is actually the way the fairy tale works. But in statistics, they were not so literate, and they thought that it was from pulling himself up from his bootstraps. So when people wore horses, there was always a lot of road horses. There was always much horse manure around. So people wore very high boots. And to put your boots on, because they're very long, you had two straps on the end, and you would pull the boot up on your foot. And the idea is you can pull yourself up out of the swamp by your bootstrap. Probably my favorite paper on this is called How to Get Something from Nothing. And this idea of bootstrapping was developed very early on for when you had limited data sets, not too much data. And this is very important in proteomics, where we're looking at rare diseases, because sometimes it's very difficult to get positive samples. So the idea is, by dividing our data set up randomly and developing multiple models, we can generate statistics that we can use basically for everything, not just for parameter estimation. And one of the things we have at our advantage is combinatorics. So if we have a single set of data with 10 objects, and we look at all the data at once, there's only one way of doing this. This is all the data in the calibration set and all the data in the prediction set. If we use cross-validation, leave one out cross-validation, or sometimes called the jackknife method, then there'll be 10 ways of doing this. But if we split the data set up equally into two halves, 5 in the training set and 5 in the prediction set, there are 250 different combinations. Now, that doesn't seem so good until we double the size of the data we're working with. If we work with 20 objects, this number jumps up to about 200,000. So a lot of times combinatorics hurts us during optimization. But if we're interested in bootstrapping, it's going to be very helpful. It helps us make sure that we get random and independent sampling from our data. The other advantage is, after doing some bootstraps, we have the central limit theorem, which means that any time we start averaging independent random variables, no matter what the distribution is, they start behaving normally. So this was generated in MATLAB, and this is a uniform distribution. And this is what happens when we start taking two uniform random variables and adding them together. Already we get something that looks somewhat normal, because it's high in the middle and low at the edges, because you're twice as likely to get a high and a low object as two high objects or two low objects. With as little as 5 bootstraps, we start getting something that looks very normal. And if we go up to 100 bootstraps, what we see is our precision becomes very good. The width of our standard deviation starts to shrink. And this is very helpful if we want to compare or evaluate different methods. Okay, so one of the very first programs I wrote as a young assistant professor was this fuzzy rule building expert system. This is a parameter-free method. It uses information theory to sort of optimize the trade-off between bias and variance. And I just have some examples coming up a little bit later, so I just wanted to introduce it. And when we were developing this and working with neural networks, we came up with the latent partition method, which was published in the year 2000. So this is one of the very early bootstrap papers. And the idea of a latent partition is to make sure that we do things that are sort of logical. We want to maintain the same distributions for our training sets and prediction sets when we do our bootstraps, because if we take all of class A and put it in our training set, and all of class B and put it in our prediction set, we know things aren't going to work very well. So I have a couple of slides that will show you how this works. The other interesting thing is to keep in mind of replicates. We aren't interested in getting the smallest precision as possible. We're always interested in the most accurate answer. So scientists generally will trade off precision to get more accuracy. And we can regain our precision by doing more experiments or more bootstraps. So we want to make sure we do this, so we generate general methods. And if we're using self-optimizing methods, we can get hundreds of external validations, not just one, using this bootstrap procedure. And when we calculate averages across bootstraps, we get normal statistics, and we can get precision bounds, and we can use well-defined ones like 95% confidence intervals. So here's an example of why Latin partitions are important. This isn't drawn, it was generated by the computer. This is a decision plane made by the fuzzy expert system for two classes. We have 50 A's, 50 B's, and two variables, and we can see it sort of splits right down the middle. But if we increase the number of B's up to 5,000, we see a shifting of our fuzzy decision plane. And the reason for that is statistics or gambling. So if we ended up in the middle here, it's much more likely to be a B than an A. So this is both good news and bad news. We always have to pay attention to the balance of our experimental design. It's always nice when we have the same number of all objects. But we can also build risk into our models by biasing the experimental design and using more B's than A's if it's more important to recognize a B than an A. And this is important in things like homeland security, where it's much more important to detect an explosive than it is to miss an explosive. So we want to make sure that we increase our false positive rate, decrease our false negative rate. Basically, this is a graphical picture. We have a red class and a B class, and we're going to randomly split it up into three equal sizes, A, B, and C, and we maintain the same proportions of the A and the A group between the red and green, the B group, the red and green, and C group in the red and green. And then these will be our training sets down here. And then once we're done, because we've used every object once for prediction, we can pool those results and get a comprehensive figure of merit for our entire data set. In other words, we're getting a prediction from every object that we collected. We're not wasting any of our objects. And this is where the idea of efficiency comes in. How we do this is if we're doing classification, we usually start with these binary encoded matrices where each row corresponds to an object and each column to a class. In this case, we have 2 in class B and 4 in class A. We usually work not with the data set, but indexes. So we segment them. So the class B are at the bottom, class A at the top. We do a shuffle, which is very easy to do in MATLAB. And then we usually generate these logical arrays that we can apply to our data set, the X data and the Y data, to select out which one we want to use for training and which one we want to use for prediction. And then if we're working with calibration, partial least squares, we have a series of numbers. They could be in any order, but we usually sort those and then work with the indexes. We reshape them, and then we shuffle the rows. So these rows get, each row gets shuffled. And then we generate our logical matrix. And now we can do the same thing for calibration problems. We want to do regression. One of the techniques that we've been working with very recently is support vector regression. Support vector machines are very fast, and the algorithm is very fast, so it's very useful. One of the things that a lot of computer scientists like to do is they like to throw the objects out during the optimization. This is usually called epsilon insensitive support vector machines. But we don't like to do that because we like to interpret our models. And by including all the data objects in our model, we can average out the effects of noise. And quadratic programming is a very fast algorithm for optimization. And it also works very nicely on multiple processors. It tends, in Windows and MATLAB, it tends to distribute, if you have 6 processors, across all 6 processors very nicely. Basically, we have our general regression formula. These are the insensitive lines, and in this presentation, this will just be 0. So these are our residuals that would go up to our line and down to our line if we make these 0. And what we're going to do then is, through a little bit of optimization theory, minimize those. So we can have a variety of different penalty functions and loss functions. In this case, the penalty function's all going to be quadratic because we're squaring or looking at the squared length of our regression vector. And then here is basically the fit of the line. And this is the key parameter that balances between bias and variance. Now, one of the nice things we can do is we can actually convert to a dual space, and this comes from optimization theory, where we work with these kernels. So what will happen is if our data has many variables and few objects, it's very similar to the principal component transform. We can drop it down to a square matrix where it's just the number of objects by the number of objects. And again, these algorithms tend to be very fast. We have to put some constraints on it to make it work, but MATLAB is, in their optimization toolbox, has the quad prog program that does this for you all automatically. These are examples of loss functions. This is a quadratic loss function. The Laplace loss function is basically an absolute value of the residuals. And then we can take a hybrid called the Huber loss function, where as we're close to the line, we use quadratic optimization. And we minimize the outliers using an absolute value. And that gives some robustness into our model building step. Okay, so we just have an example with PLS coming up. So again, this work was published in the 1990s. But the idea is we're going to do bootstraps, calculate an average prediction error, and minimize that error to determine the number of latent variables to use with our full data set. And this tends to work very nicely, and it makes a good reference method for us to compare other methods to. In this example, we have a synthetic data set. We have 1,000 variables, and I think it was, 150 objects of 3 classes. And we added a lot of noise to it. In black is our ideal signal. This is a nice part of synthetic data. We always know what the signal looks like. So we can develop an ideal model just simply by building a model from the signal itself. And it may be hard to read these, but they're all basically the same for the coefficient of determination, the R squared on the prediction, 0.985, 0.985, 0.985, and 0.985. These are the coefficients. You see there's a lot of noise embedded because the variables are correlated. Okay, so one of the things we can do with support vector machines is we can insert matrices in here, and these are tri-diagonal matrices that can calculate derivatives. And the interesting thing in the primal space is everything is always the opposite in the dual space. So here what we're actually doing, these are Lagrange multipliers, and we're actually maximizing those. And then down here we're interested in minimizing the function up here. But anyway, I'll show you what these K matrices look like in a minute. So let's go back and see how well things work. This is our bootstrap method where we used 10 bootstraps and 4 partitions. And you can see these error bars are 95% confidence intervals. And what we're doing is optimizing the cost function C in our model. This is our calibration error. So whenever we're doing numerical optimization, we have to have bounds. So the way we set our bounds is we use our calibration error from where the calibration error starts to decrease and where it sort of levels off as it goes to 0. So we know in here and in here there must be a minimum for the prediction error. Because we have synthetic data, we were able to generate 50,000 other validation objects using the same recipe to generate the data. And what we see is that the minimum in our bootstrapping is very close to the minimum in terms of our validation set as we modify the cost function. So that's sort of a reality check to make sure that things are working nicely for us. Now, this is the K-matrix that we're using, and if we go to the dual space, we have to invert it, so that's why there's a -1 here. And I multiplied it by 10 just to make these numbers a little bit larger and easier to plot. If we put this inside our weight vector as a penalty function, it has a smoothing effect. So now we've gotten rid of all the noise in our model. It's still not perfect, but we're getting much better fits when we look at the R-squared values. So we're at 0.985 here, and then we jump up to about 0.990. So we get a small incremental increase. But this makes it much better in terms of chemometrics because it's easier to interpret the loadings. We start getting regression vectors that resemble the features in our data. Here's an example of using single beam near-infrared spectroscopy. I think a lot of you are familiar with near-infrared. And there's no reference here. And we're looking at it as glucose and cow plasma. This is the principal component plot, and we'll notice that there are 4 clusters of data objects. And these 4 clusters are from 4 different cows that they were using in terms of the sample set. And if we do leave one out, cross-validation for partial least squares, it turns out we actually get 2 minima. We get one here around 13, and then we get another one over here that are equal. So the question comes up, which one is real, or which one should I use? And a lot of times, leave one out cross-validation is an insufficient method. That's a statistical sense, the word sufficient, because we get overfitting in our model. But if we do bootstrapping, we find a clear minimum here. Again, you can see the error bars are very precisely, fairly precise. They're 95% confidence intervals for the partial least squares result. But it makes it very easy for us to find the minimum. When we do the support vector machines, and again, in this notation, it means we have 10 bootstraps and 4 partitions. Using the Laplace loss function, we lose a lot of convexivity to our optimization, and it's possible to get multiple minima. But the minimum's located right here, and here are 95% confidence intervals across each cost parameter for the 10 bootstraps. If we go to a quadratic loss function, things tend to behave much nicer. We're a little bit more precise near the minimum, and we get a nice quadratic response that we can optimize fairly quickly. And then this is showing the Huber function, and you can see it's sort of a mix of the Gaussian function and the Laplace function, which should be expected. Just an example of what we get. Here are our calibration objects, and again, it may be hard to see in the back, but we have 95% confidence intervals on every object for calibration and for predictions. So this provides some very useful information. Here are the regression coefficients on the glucose data, and if you look at it, we get fairly high coefficients of determination, 0.991 for the support vector machines, but they're fairly noisy looking, right? These would be very difficult to interpret, again, because we have all this correlation. When we use our tridiagonal matrix to sort of smooth things out, we start getting improved prediction rates. We're up to about 0.992. And then here, again, is just for reference, the partial least squares where we still have the embedded noise inside our data. And Laplace actually went up to 0.993. Okay, so this got us through the optimization part. Let's look at validation. So some things that we can do is we can use match sample statistical tests for each paired object inside a bootstrap. This is a very powerful method for comparison. I'm going to show you that when we use single validation sets, sometimes we get contradictory results based on how we pick that validation set. And there are several methods for doing this. So we have 2 examples where we have basically the same distribution of underlying objects, and we're just changing the noise or random variables that we're adding to them. And they're going to be labeled as data set 1 and data set 2, and we are comparing, in this case, classification for the fuzzy rule building expert system, PLSDA. So if we do random splitting into training and prediction sets, we can see that in some cases we can get very positive results. And in other cases, we get lower results, even though these distributions, the underlying distributions, are identical. But if we do a comparison here, we would conclude in both cases that the fuzzy rule building expert system is working better than partial least squares. This is another way of splitting the data. It's very similar to the Kennard-Stone algorithm, but it takes into account the Y variable, so it maintains the balance between the training set and the prediction set. And I have a reference at the end of where the code is, where we downloaded it. In this case, we get a value. So if we use this method for splitting the data, we would conclude that the fuzzy rule building expert system is working worse than partial least squares. And same thing for our second set of data. So based on how we decide to split our data and create our prediction or validation sets, we get two entirely contradictory results. When we do the bootstrap Latin partitions, we average everything out. Here's our 95% confidence intervals, and we can see that things are agreeing much more, except in this one case for partial least squares. Because this is synthetic data, we can make our 150,000 different validation objects, and the other important thing is to see how well we agree with our larger validation set, and we get, for the most part, very good agreement between our bootstrapped result and the validation set that we're using to characterize the distribution of our data. Let's look at some real data. This is some ginseng extracts that we analyzed by UV spectroscopy on a plate reader. We have 6 groups. We have Panax ginseng, which is the Chinese species of ginseng. Panax nota ginseng grows in northeastern China and Korea. Panax quiniquefolius is ginseng for the U.S. And then we have U.S. ginseng, that species. This species here grown in Canada and in China. And then we have Chinese ginseng that was bleached. And this is what the principal component plot looks like, just showing the distribution of our data. Again, work was done with our U.S. Department of Agriculture, so we didn't have much control over the number of objects. It was all based on the availability of our samples. In this case, we look at the minimum. We did 10 random splits, and we look at the minimum values and the maximum values. And again, we get some results that are varying quite a bit. These splitting methods that are look for data that only interpolates usually give you a very positively biased result. And we can see that where we get 100s here, 97 here, and 94 here. These are the bootstrap results. And for validation, we use 2 separate plates. So we use one plate for calibration, and then the other plate for validation, and then we would reverse the plates. So it's not the perfect set because we only have 2 validation sets, but this is showing the average of the results when we use these different plates for validation. Another example is some data that John Clivis put online and generated, which is near-infrared spectroscopy of wheat. So we did some multiplicative scatter correction and subtracted the average is all we did with the data. This is showing a comparison between partial least squares, where we used the monitoring set he provided and the validation set. And this is where we threw away the monitoring set. We didn't use it at all and just used our super partial least squares algorithm. And you can see the results are very comparable to one another when we use the 2 methods. But we use less data here, so we gain in efficiency. Up here, we have the results from these. There's a lot of information in this table for these different data sets. I want you to focus on the standard error validation using the validation sets. Up here, we use the monitoring set. Down below, we use the bootstrapping to optimize the model. And here's where we use the bootstrapped Latin partitions. And these two are in bold are significantly different. We were able to do a paired sample t-test to compare to the partial least squares. So even though if we add together the confidence intervals, it turns out that the 0.008 and the 0.009 get us exactly at 2.217. Doing the statistical test can really clarify whether we have a real difference or not. Down here, this is moisture up here, and down below we have protein. And this is even more remarkable that even though when we compare the confidence intervals, the averages, they appear to overlap, when we do the internal match sample t-test, they were statistically different between the Huber and the Gaussian support vector machines versus the partial least squares. So if there's a lot of ambiguity when you're comparing methods, a lot of times that may be due to the validation that you're doing and not necessarily the methods. So by using a more statistical-based approach in comparison, we can tweeze out smaller differences between methods that you might not normally see. So the other thing I want to point out is when we use these super methods, you can see that every object is used for prediction in red and in blue for calibration. So this is what I mean by we're making good use of our data. And we can see how precise each sample is, and that can help us find samples that are problematic. We can go back and see if something happened during that sample collection. The validation errors are relatively low, but, these are standard, no, these are the R-squared value, yeah. So they're relatively low, but we can start doing a comparison and we can sort of see how the different samples are responding within our model. Going back to our bovine plasma experiments, we did the same thing. So here is our super PLS. I just included one of the support vector machines, the Huber over here. This is again using our K matrix. So now we're looking at the loadings, and we can also plot the confidence intervals in red and in black, and that usually tells us which features are going to be important or not. If they extend beyond the confidence interval, we usually know it's fairly important for our model. If we look at our standard error of validation, we're at 1.16. Here, 1.17, so that difference is going to be very close, but we're able to smooth out these coefficients and assist in our interpretation, be able to put some of the chemistry back into our chemometrics. So, in conclusion, let's see, I think there was one more thing I wanted to say about this. Okay, so going back and using the bootstrap validation, one of the things that we found was that there was no statistical difference, even though there's a marginal difference in having a slightly lower standard error validation. When we applied the statistical test, we had a p-value of about 0.8 or 80%, which told us that there was no difference between methods. But we do like this method, and we applied this technique for the shootout. So I'll find out maybe this afternoon sometime how well it worked. So in conclusion, bootstrapping is something that I would encourage everyone to at least try, because it allows you to make efficient use of all the data you collect. Some experiments are very expensive, especially either with obtaining samples or instrumentation. Latin partitions preserve the a priori probabilities, but these are very important in developing a model that works. So you always need to think about the construction of your data before you start doing your applying your methods to make sure that it's really giving you the information that you're after. Subset selections such as Kennard-Stone and SPXY prevent extrapolation of predictions, but they tend to give you positively biased results. So if you're interested in predicting the future, you're much better off not using these methods. And that's my own opinion. Hundreds of external validations can be obtained by a nested approach. So by incorporating an internal bootstrap and then an external bootstrap, it requires much more computation, but personal computers are much faster now. You can certainly do this in an hour or a couple of hours based on the size of your data set. And this actually really assists in getting new students to hit the ground running and generate papers, because you don't have to train them in the model optimization step. You have average results that are reported. along with confidence bounds for prediction and calibration objects, or any figure of merit, R-squared values. We can calculate confidence intervals and know how many sig figs we should be reporting our data with, and loadings. And the best part about bootstrapping is because they're independent, they can easily be distributed across multiple processors. So this technique will just get faster and faster in the future as the operating systems become better and better at distributing workloads across the processors that are available. Lastly, I'd like to include my students that did most of the work in the acknowledgments. German Zhang published the SPXY MATLAB function. He's not the author of the technique, but he put it online and made it available. Gary Small donated the near-infrared data of the cow plasma and glucose. John Kalaivas for the wheat data that he makes available to everybody. We're working with a company in Colorado that works with cannabis, so they have this name Canaprint that has sponsored some of our work. U.S. Department of Agriculture, their Agricultural Research Service, they also sponsor the work. And then I included down here the two sponsors for this meeting for their generous invitation. So with that, I'm happy to answer any questions if we have time, and if we don't have time, you're free to find me during the day.
Thank you very much, Peter, for this nice presentation. Is there any question for Peter? Raise your hand. They are all shy.
Okay, well, you invited me one-on-one to ask questions. So
I have one question.
Okay.
I will take the case of PLS.
Yes.
When you have this SPLS,
Yes.
and compared to the normal PLS, the final model, what's the difference? Because you have to use all the samples.
That's right, yeah, so we use all the samples, but we've now determined the number of latent variables to use.
That just the difference between PLS and SPLS is just the number of factors.
Yeah, so what we've done is we've just bootstrapped. It's very simple. We just use the bootstrap. Maybe I should, we just use the bootstrap to calculate the average prediction error for each latent variable. And PLS is very fast because we can build a very large model and then just vary the number of latent variables when we do the prediction. So when we find that minimum, that's what we use for the entire data set. Now, as you may know, they've also done some work where people have used the F statistic to try and reduce the number of latent variables when they're calculating the prediction error. But because we're using a larger data set, this sort of works out naturally for us with the PLS by just finding the minimum, because we've tried using the confidence intervals too to see where the minimum, the prediction error was above the minimum plus the confidence interval, and that didn't work so well. So.
And when you show some result about validation, you say external validation.
Yes.
How do you choose the samples for this external validation?
Okay, well that's a very good question because that's the whole underlying theme of what I was talking about. We use every sample for the external validation. So because when we're building our models, we never use these samples for each, within the bootstrap for developing the model or the pre-processing, right? We have to keep everything unbiased. Then that set gets used for basically validation. And because we're doing this multiple times and pooling it, every object gets used for external validation, multiple times.
It's like leave one out then.
It's similar to leave one out, yep.
Yeah, so you overfit the triazole.
Yeah, but
okay.
We're just doing it many times, and we're doing it systematically, so as opposed to just leaving one object out and not having any measure of precision. So, simple idea, something everyone can try.
It's a little bit different than external validation because you turn inside the same data set, in fact.
Yes, yeah, so it's one data set, but because we treat the objects independently, they aren't used in any part of the model optimization, it's equivalent to an external validation. Yeah. So.
Okay, thank you. Another questions?
First, I would like to thank you, Professor Peter. I have two questions.
Okay.
The first question is about Bootstrap. I noticed that whenever the people would like to apply Bootstrap, in order to apply PLSDA, they use only 2 categories. Can I apply it on 3 categories or more?
Yes, you can. So one of the examples, we use 3 categories for this
that's nice.
data set.
And second question, if I have multi-way data, can I apply this Bootstrap and how?
What
If
kind
I
of data?
have multi-way data.
Multi-way data?
Yeah.
Yes, so you can basically apply it to anything. So as long as you have the method, what you're doing basically is just dividing your data up,
Yeah.
and then you're going to process it using your multi-way method. Maybe Parafac is what you're using. Or,
Yeah, that's it.
yeah. And then you build your Parafac model. You generate your figure of merit, right? And then we go back and then divide the data up into, randomly, right? So this is what makes sure that each set of evaluations is independent. And we like to do it systematically so you get to use all your data.
Okay.
So it's just basically thinking about how we develop our subsets for model building and model validation. And if we can do this, build our models without requiring the validation set to optimize the model, then it's independent, and we're effectively doing an external validation, right?
Okay.
So it's very important that we don't corrupt what we're doing by sort of cheating and using our validation set to tweak our model, right?
Okay, thank you.
You're welcome.
Okay, I think we have to go. Peter, thank you again.
You're welcome.
Thank you.